going to start.
She started.
Yes. So welcome everybody to the online seminar series, Machine Learning Needs Mathematical Optimization. We are very pleased to have today Yael Grushka-Cockayne. She is a professor of business administration at the Darden Business School, and she is also the senior associate dean for professional degrees programs. Her research and teaching activities focus, among others, on decision analysis, data science, forecasting, and behavioral decision making. She has served as a consultant to international firms in edtech, aerospace, and pharma industries. And she is an award-winning teacher and was named the 21st Thought Leader Professors in Data Science. So she does also service for the community. She is an associate editor and management science, operations research, decision analysis, and info journal of data science. And she is currently the president of the Decision Analysis Society at Informs. So we are very pleased to have you today here. For the audience, please remember that Yael is happy to take questions on the way, so you can put them on the chat and we will pay an eye to the chat. And if not, at the very end, we will also open, say, cameras and microphones. So thank you, everybody, for being here, and thank you, Yael, for offering your time.
Dolores, thank you so much for inviting me. I'm excited to be here. I'm very excited to get to know this community even better. I've been following online a lot of what you've been doing over the years, and I know that the work that gets presented here is influential and important. Let me just share my screen. I want to make sure that I can do that. I'm going to share my screen, and I'm going to talk to you, as Dolores said, about a topic that relates to decision analysis, which is my area of expertise, specifically forecasting and the wisdom of crowd. I'm going to talk about combining expert opinions, and I will do my best throughout the conversation to link it to data science and to link it to domains in which I believe this work will be relevant to some of the participants. But I also know that there's a broad set of interests here, and so we're gonna make sure that people understand and people can be inspired to use these tools outside the context of this talk. I'm trying to share my screen, and of course now, even though we tested it, it's not working. Let me just make sure that, give it one more try, and if not, I'll use my other computer to try and see if I can do it properly, but I want to make sure. Let me give me 1 second here. Now it's looking good. I'm excited. I feel like I can do this now. Okay. I think I'm sharing now. Yes? Okay. I think I can share. I see it. So I think that I'm sharing. Dolores, I guess you guys can see it too.
We can see it perfectly. Yep.
Perfect. Okay, great. Folks, I have my surface on the side that I'm going to be using to annotate. I have my big screen so I can see your names and your hands. I can see the chat even. So I love to make this interactive. So if you have any questions, please type them in. Either I will notice them or Dolores will notice them, and we will try to get you some answers. I will try to finish with a few minutes spare to give folks an opportunity to ask questions. And please feel free to reach out, LinkedIn, Twitter. My email is easy to find. I love engaging with participants beyond this, this webinar, and I would love to hear your feedbacks and thoughts. It always improves the work even further. I'm going to talk about, in general, challenges of combining forecasts. I've done a fair amount of work in the field of wisdom of crowd, and this talk will be squarely in that kind of vein, in that line of literature, and specifically when the experts are correlated. And as we're going to talk about pretty quickly, it turns out that that is a pretty common setting, or in many instances, we expect our experts to be highly correlated, whether we're talking about subjective human experts or whether we're talking about forecasts from various machine learning models. There is a high, in many settings, we're expecting to see some correlation among our experts. And the main kind of headline of this talk is, if you're combining multiple experts' opinions, multiple forecasts from multiple models, take a moment to think about how correlated they are, and you may want to take that under consideration when you decide how to aggregate those opinions. Again, I'm going to start with some very applied context and examples, and then I'll get into some of the results in a paper that my talk is based on. This is joint work with David Soul, who was a former PhD student of Jason Merrick, my other co-author. I was on his committee, and this is a result of his work. This is David's second career after a very successful career in Capital One, and he's now teaching at the University of Richmond, and Jason is from VCU down the road. So both in the areas of decision analysis, and it was a real joy to work on this project. And it is forthcoming in management science. So there is a paper, actually, it's out there on SSRN, and also we just got the paper page proof, so it will soon be in print, which we're very excited about. Okay, so far we're doing okay? Making sense so far? Okay, one of the most common settings in which this kind of work is inspired by, and a very famous set of papers actually, is based on the story of Sport Obermeyer, where there was a question as to how to predict demand of a seasonal product when demand is unknown. And the proposal, which interestingly has gone back and forth in terms of inspiration from practice, has always been, okay, I'm going to collect various estimates, and I'm going to use those various estimates to make certain statements about my expected demand. But more than that, I'm going to also use the pattern of the various estimates to not only make statements about the expected demand or the median or some central tendencies, I'm also going to learn and make certain statements about the variance that exists in my demand. And I'm going to look at various pieces of information that I can collect about these estimates, maybe from historical estimates and how well they did, to also come up with some kind of notion of expertise. How well is each one of my experts giving me estimates of my upcoming quantity of interest? So Sports Obermeyer is one instance. We all know kind of examples around us, and I'll talk in a moment about other settings in which we collect many different estimates on a regular basis. We do something with those estimates. We rely on the crowd to inform us as to what we should be doing. And then we try and adjust. We try and use that to kind of make a prediction for the future, use that to make the best guess that we can about what the distribution is going to be, what the central tendency, what the distribution is going to be. And we make decisions, typically operational decisions, financial decisions, marketing decisions, HR decisions based on those estimates. So in the Sports Obermeyer case, which I encourage you all to read, the forecasts there were for the demand for these various fleas and jackets. For those of you who ski, I think some of you did some skiing during the iForce conference down in South America. So if you were to guess the estimate, I can get various guesses from the folks in the call, and I can do something with those estimates. So if you forecast even either the sequence of demand, which would be the most popular. I think this will be the most popular. Probably not. I'm the only one that likes those kind of crazy patterns. Okay, so I think this is going to be my number one most popular model or type of jacket. This is going to be my number two most popular jacket, number three, and number four. I can use some kind of ranking to create some kind of hierarchy and to come up with an estimate, or I can actually try to predict the quantities at a store level, at a SKU level, at a regional level, or even at a chain level. Oh, I think there's going to be, let's say, 150 of these in demand. I think there's going to be 120, maybe 190, and so on. And that's just my estimates, but I can collect that from, let's say, 10, 20, 30 other judges. And then I can do something with that information to come up with a prediction for how many of each kind to order. Pretty straightforward use of wisdom of the crowd. And we see that the notion of making predictions in the context of uncertainty around demand was always very important, but it has become even more important and more critical after COVID. In addition to that, wisdom of crowd in retail is just one setting that has been popularized and increased in its kind of need and increased in its visibility and in terms of the sophistication related to the techniques that have been developed, but it's definitely not the only environment in where we see a collection of opinions made about an unknown quantity and some aggregator or decision maker putting those ideas together. What has especially been interesting over the years is that, one, there is this notion that some of my experts are more knowledgeable than others. I, for instance, never ski. I don't typically buy these types of fleece or jackets. And so you may discount my input to this process. And maybe you'll look historically to say, how many times has Yael participated? How many times have her predictions been accurate? And then put a certain amount of weight on my opinion versus, let's say, Dolores. I think, Dolores, you're a skier. Are you a skier? Do you ski on a regular basis? Maybe no, she says no. Okay, still, she still is, like me, a little bit more Mediterranean in our weather orientation. So maybe we don't ski as much, but maybe some of you online do have some inside knowledge, and you would predict it accurately. And I could see that you are pretty skillful in your capability, and maybe I would put more weight on what you say in terms of your prediction for the quantity of interest. And therefore, when I combine these opinions, I'll put more weight on some and less weight on the other based on some kind of historical pattern of performance. Now add to that a layer that says, not only am I going to differentiate the weights, I may also consider whether certain experts in my crowd, certain individuals that I'm collecting their opinions, are correlated with each other. Meaning, if I have two people like myself and Dolores who are unknowledgeable or less skillful, but we're highly correlated with each other, should you put more weight on us or less weight on us? If you have two experts who go to the same ski resort every year and they experience the same view of the world, let's say somewhere in the Alps, and they give me two inputs, and they're pretty good, both of them over the time, they're pretty accurate in their predictions. Should I put more weight on them because they're correlated, or should I discount them because I have too much of the same opinion? That is really what is going to be at the heart of what we're debating. And you'll see that we're going to try and come up with techniques that address that correlation issue among them. And so we're going to move from talking broadly about the wisdom of crowd to specifically thinking about the challenges that come with this process of me collecting from, let's say, several of us. Let's say I have several estimates, 150, 120. Let's say somebody predicts 300 and somebody predicts 90. I can use this information and I can say, okay, I want to take a simple average of that, or I can selectively put some weight based on historical patterns that these experts, if I have, let's say, expert 1, expert 2, expert 3, and expert 4, I can put weights based on their expertise and capabilities from the past. But there are some challenges that come up with this process. What are some challenges? Well, one, subjective assessment, if it comes from an expert, could be flawed, meaning not all predictions come from machine learning or data science or tools and sophisticated algorithms that some of you may deploy. So if it comes from machine learning, we'll talk about some problems there too. It doesn't eliminate some issues, but it could very well be that these are subjective expert opinions, and there could be some questions that come from those subjective expert opinions. And I see that there's a hand up. I'll finish the slide and then I'll pause for a question in a moment, if that's okay. So subjective assessments can be biased, they can be overconfident. If it's a point estimate, they can really be volatile, they can be inaccurate, they can have their own shortcomings, and we need to be thoughtful as to what kind of characteristics come from subjective assessments. Sometimes experts don't feel like they can give us exact quantities of interest. So for instance, if I'm trying to predict demand, sometimes folks cannot actually give us the demand, but they might be more comfortable ranking these different uncertainties. And we need to understand how to process rankings. And I'm working on a couple of projects right now that are looking on how to do the wisdom of the crowd when we're dealing with rankings only, or ratings, and we're not dealing with actual point estimates on the same scale. In addition, and the real focus of my solutions and my proposals today are going to center on this notion of correlation. implying that when I go out and seek a crowd, seek many inputs to my uncertainty and seek many forecasts, those forecasts might be correlated as I just described. And sometimes that's because they're just happen to be correlated for many different reasons. The most commonly cited reason has to do with what's called the shared info problem, meaning if experts have the same underlying information, they're relying on that same information to form their prediction, and therefore there will be an overlap and a redundancy in shared information in my aggregate. And so I need to think about how to deal with that notion of correlation. I'm not getting as much of a variety of inputs or a variability in the inputs, and I need to adjust for that in my forecast or in my aggregation process, I should say. Social influence in some settings where these forecasts are given in a more open manner, where folks share with each other their opinion, and there's maybe a Delphi approach or more of a kind of group approach to decision making in a corporate setting. For instance, in the notion of, let's say, Sports Obermeyer, if they go out and seek input from all their sales manager and all their branches, there might be a social influence. It might be that I have some reputation to protect, and I care about where I stack up. And so therefore my social influence will again influence my input to the process, and the aggregator needs to take that into account. And another aspect of the process that I am going to talk about today, and it will kind of come into play with the correlation, I'm going to talk about both of these, has to do with small data. And what do I mean? Again, dealing with data scientists, it might not be obvious why small data is even a problem this day and age. But in our context, it's all about, I need data here to estimate performance of my experts. If I want to give more weight to an expert that is accurate or has shown that they have skill related to forecasting the quantity that I'm interested in, I need historical information on their past performance to understand really how skillful they are. The problem is that sometimes in these contexts, experts that give me forecasts come and go, or they're not persistent, or they don't always give me a submission, they don't always give me an estimate. And therefore, I don't have that much information to rely on when I assign a skill or try to kind of determine how reliable and how knowledgeable and how skillful they are to give them more weight in my overall aggregation. So the small data problem has to do with a history of performance per expert, which we may not always have. And combine that with correlation, the combination of these two is going to present some challenges that we in this project try to tackle straight on and propose some solutions for. I'm going to pause there. Dolores, I thought that there was a question. I don't know if we have an opportunity to either get the details of the question.
No, we didn't. So I think we go ahead. Yeah.
We move on. Okay, no problem. Again, if you have a question, you can put it in the chat, send it to Dolores, or raise your hand, and we will try to get the question answered. So hopefully folks understand the setting that I'm talking about broadly. I'm going to get into some more detail. If you've read about the wisdom of the crowd, then you're probably familiar with this line of work. If you're interested, what I'm going to talk about really is going to center more specifically around this puzzle. It's called the forecast combination puzzle, which has been well documented, which basically says we are tempted to use very sophisticated tools to aggregate forecasts and to combine them. But often we find out that a simple average does good enough. And you'll see in my talk why that is. It has to do with both of these issues, the correlation and the small sample size result in the simple average outperforming more sophisticated tools in practice. And we're hoping to add to the toolkit another method that should perform well. And I'll give you some insights as to why it performs well, and even give you some empirical results trying to prove it. Okay. So again, we're focused on aggregating forecasts, and I'm going to start kind of presenting the setting a little bit I have some notation, but I try to minimize it to make it intuitive. There are results in the paper. Again, you can either send me a brief email or download the paper. Hopefully, some of you maybe have sought it out. But if you're interested in some of these more formal results, all the proofs and everything are available. And I'm keen. I already know of some use cases of this in a broader setting of forecasting, machine learning, time series forecasting, hierarchical forecasting. So there's some work that is being done that is interesting follow-up that I can mention a little bit at the end. Okay, so what is our setting? Our setting is we have K experts or models. Okay, so remember, this can be models, this can be machine learning forecasting models that provide a forecast for a quantity theta that is unknown, and that's the quantity of interest, maybe demand of a certain jacket or a certain fleece. We do have a history of forecasts from these K experts, and we can use that history to come up with some assessment and some information around the skill of an expert, which is 1 over the standard deviation, really kind of based on what we believe is the variance in that forecast's error. And you'll see that at some point we start to use estimates for that, and you can already maybe see where we're going to have a little bit of a bias variance issue going on in order to come up with our estimates for some of these parameters. And so we have a history of forecasts, we have experts with certain skill sets, and then we also have errors that are correlated among them. And our rho ij, in theory, if we knew it, we would have a rho ij, some kind of correlation between expert I and expert j, typically positively correlated. You'll see that in reality, we get a little bit of negative correlation, but most often we see positively correlated experts. And our question is really pretty straightforward and simple. All we want to do is how do we combine these opinions and these forecasts, or in time period, current time period T, or whatever you want to call it, how do I take that information and combine it to come up with the best possible forecast that I can? Okay. In the past, I mentioned this briefly, but I'm going to put some formality. There's been there's been a lot, but there's been 3 main proposals out there for how to aggregate these types of forecasts. Simple average basically ignores the history and says, I'm just going to put equal weight on everybody. So WI, that is just a matter of 1 over the number of experts. So equal weight on every single expert in my pool. Variance weights that use the history of the performance and says, if you're more skillful, you'll get a higher weight. If you're less skillful, you'll get a smaller weight. And then finally, there's been a proposal, and very well known, and I encourage everybody to read it, Winkler's 81 paper, which, and Bates and Granger's paper is also very well cited and a critical paper in this field, that basically show us that there's an optimal weight that we can calculate in order to minimize the error by taking into account not only the skill or the variance, but also taking into account the correlation among the experts. And those are the covariance weights. And these in theory, perform the best. However, what has definitely been true is that it's been shown over the years that those theoretical weights, those covariance weights that take into account all the information that we would like them to take into account, it's been shown that it actually doesn't always perform well in practice. And so the issue is that it requires a pretty large set of historical performance by these experts to come up with those estimates for the correlations. Otherwise, we get estimation error, and the estimation error by far outweighs the benefit from using the covariance weights, and their impact, or their how well they perform, decreases quickly the more estimation error we have. And the fewer data points and the fewer past performance data points we have, the more error noise we're going to have, and that affects our estimates. And this has to do with that estimation, or that combination puzzle, that tells us that as sophisticated as our tools can be, at the end of the day, a simple average in practice works well. And at the heart of that is the issue of the estimation process. And again, the estimation issue and the errors related to estimation are going to be more pronounced when I have correlation and when I have little data. And so those are, again, the 2 settings of which this paper focuses on. Okay, so that's what we're trying to play around with. We're trying to play around with the bias. So the simple average will suffer from bias because it's simplistic. It doesn't take into account skill, but it doesn't have estimation error. And the correlation based or covariance based weights that have a much larger degree of estimation error, even though they can be much better in terms of theoretical, eliminate the bias. And so our proposal, and again, this is a fairly simple message, which is kind of cool, I guess, to have in a paper. And I'm happy that we kind of, it helps me focus on that. Our simple proposal is kind of to slot something in between here. It's to say, well, we can kind of come up with a little bit of a compromise. We understand that covariance weights are more comprehensive. They account for all the correlation. They should be better in theory. But because of the estimation error, we don't want to go through the process of trying to estimate every single pairwise correlation. It's just, it opens ourselves up to too much noise. Too many parameters need to be estimated, and that is going to basically deteriorate the quality of my combined forecast if I don't take that into account. And so therefore, our proposal is, okay, what can we do that is kind of a little bit of in between? We can come up with an estimate that is a common correlation, a single estimate of correlation, really still work with the variance weights, but kind of adjust for this notion of correlation by assigning a common correlation, one parameter, not pairwise correlations, not all of these pairwise correlations that we have to calculate, but a much clearer message around a single correlation that we can estimate, one common correlation that we would have to estimate that would basically minimize the amount of error that we might face otherwise by having from the estimation process. Okay, so simple option, and here it is even in, I'll present it in terms of the notation and how this looks like. So basically we are adjusting here for, you know, if I go back, and I don't want to go back and up and down so often, but in this matrix, basically, instead of using the row ij, which had to be estimated for each pairwise, we're replacing that with a row c, which is a common correlation, which basically says one correlation for everybody as opposed to an individual or pairwise correlations. And let me just make sure and make clear here, you see it in this slide, you see the pairwise correlations, and we're basically eliminating by a pretty sizable amount the number of parameters that we have to estimate. And in this table, I think this has to be over 2. It's not equal to 2. It's divided by 2. It's k times k minus 1 divided by 2. So a very large number of pairwise correlations. Okay. So hopefully that's clear that all we're doing is we're proposing a method to reduce the number of parameters that we estimate and to simplify the estimation process to minimize the error that we get from all the pairwise correlations, but still give some weight to the notion that the experts are correlated and to adjust for that in our aggregator. That's the plan. I think I covered all of this. What I'm going to show you in the next few slides is, first, I'm going to show you a theoretical optimal. Like if I knew all the parameters, if I didn't have to calculate or estimate anything, in theory, what would be the optimal row C that I can find? So some kind of optimality idea, knowing or assuming that we know the parameters, that's going to be kind of a theoretical optimal just to show us what's possible. And then we're going to come back and say, well, in practice, we don't know some of these parameters and we're going to have to estimate them. So we're going to come up and propose various estimators from the data, and we're going to show a couple of Bayesian estimators, and then I'll show you some empirics that just compare and contrast the performance, a little bit of a mini horse race here, just to kind of prove that in theory this does perform well under certain circumstances. And if I have time, I'll also maybe suggest those circumstances, and the paper gives detail on when do we expect this method to work well and in what environments we expect it to not work as well. So far, Dolores, everything good? Okay, I see your head nodding. That's reassuring. Fantastic. Okay. So another thing that is important or helpful to kind of consider, what we tested kind of extensively and what we noticed is that there are many different circumstances that we believe that this method can perform well. And let's talk about these two figures here that you see on the slide. I'm going to start with the figure on the left, which is all the cases where there is hope, or why I believe our common correlation approach might work. And then the figure on the right is some kind of, not warning, but it also suggests that there are some edge cases or some circumstances where we won't offer some benefit. And those are cases where our method will not perform well. And so like any other method, we want to be very clear that this method is going to be useful in some circumstances and very useful in some others. But indeed, it cannot be used across the board, but we need to be selective and more sophisticated in our kind of acknowledgement of the environment in which we operate. So what you see here on the chart is an example where the x-axis shows you various parameters for our common correlation. So our common correlation can be anything from 0, no common correlation, to or common correlation of 0, so independence, versus all the way up to 1, so positively inclined common correlation. And on the y-axis, we have the variance for the combined forecast. So what is the variance when I combine putting a certain weight on each expert? And the goal is to get low variance. So our hope is that the combined forecast has low variance, meaning not much error in it compared to the underlying quantity of interest. And you can see that our simple average, so just assigning equal weight here is on top. In this image, the simple average performs the worst. So it has the highest amount of variance, or the largest variance, I should say. Variance weights performs better. And this is a theoretical circumstance in this figure on the left, where covariance weights, if we knew the covariance, if we knew the correlations, if we knew all the pairwise correlations, and we could calculate it, the most bang for our buck in theory, this is the Winkler 81 result, would give us the lowest variance. What we can show is that various values of our common correlation do improve beyond the variance, mean reduce the variance beyond the variance weights, and get close, almost actually, get as very close to the covariance weights as possible under certain values of the common correlation. But of course, that if we don't choose the common correlation value correctly, we could actually result in worse performance, and we need to demonstrate, and we'll provide some conditions under where we can find that common correlation. But this kind of gap here between the variance weights and my covariance weights, that gap gives me the hope that it will be useful, meaning under certain circumstances, I can actually get as close as possible to the covariance weights and potentially, which I'll show in a moment, overcome some of my estimation error problem. What the figure on the right shows is that depending on the parameter settings, and we characterize them in the paper to some degree related to low correlation among the experts, so kind of conditions that we're not necessarily focused on, it is the ordering of these weights changes and the common correlation no longer performs well. And so these are circumstances in which we would not recommend using this method, which should be also helpful for the community or decision makers who use this approach to say, we want to identify when is this method beneficial and when is it not. Okay, so inspired by that, our first result does present basically some kind of insight as to when this method would be beneficial. So when do we stand to improve the combined, or improve meaning lower variance for the combined forecast? Under what circumstances would we come up with an improved estimate using our common correlation? And really, this has to do, and this gives us a little bit of a hint that we study extensively in the paper, that actually, what does this depend on? This depends on kind of the actual pairwise correlation. So like, how correlated are the individuals? And the higher this is and the more positively correlated they are, the more this condition will hold. Something to do with the skill, how skillful the individuals are, but also how skilled on average they are. And so it tells us a little bit that under pretty broad conditions, this will perform pretty well, and we can expect to see some kind of improvements. And this kind of basically says that there will be a common correlation that can yield this improvement, right? So under these conditions that are not that hard to satisfy, we will have a common correlation that would yield an improvement. And our next result will tell a little bit more. And again, these are kind of theoretical results, assuming that we know the parameters. And so I'm just going to go on and present the next result, which is another. I don't know if you guys can see it. I feel like some of it is getting cut out on the bottom here with the presentation, but hopefully folks can see it. And if not, I can send it around later. But this really shows, under the circumstances that we know the parameters, this is kind of a theoretical optimal, under the circumstances where we know K, the number of experts, that one is the easiest to actually know. Under the idea that we know the pairwise correlation, harder to know in practice, and we know their skill or their variance, and therefore 1 over their standard deviation, which their individual skill. Again, in practice, we don't always know this, but we're estimating this. But if we were to have these parameters and to know them, we could find the optimal common correlation, which is of this form that gives the minimum variance for the combined forecast. And it follows this form. This form looks a little bit messy, but it's actually pretty straightforward to calculate, given that all the parameters are available. And we even present some optimality conditions in the paper that say, when does this hold and when does it actually provide the minimum? And it's, again, not hard to satisfy, because we really show that as long as the weighted, what we call the weighted average of the experts' pairwise correlation, which is, it's in this row W that's detailed in the bottom that is cut off there. It's kind of a weighted average, if you will, of the pairwise correlation. As long as that's positive, which very often it will be, this optimality condition will hold. And so it's not too hard to satisfy in theory. In reality, we don't know these parameters, so it'll be harder to use. But it gave us some hope that this method has some grounds to build on, because we can see that there are circumstances where this very common, easy to satisfy circumstances where this optimal common correlation would hold. Okay, so from there, where do we go?
Yeah,
in reality, yes, go ahead.
There is a question in the chat from Felipe. Can you see that, or do you want me to read it out?
How is this estimator, the covariance matrix, related to the shrinkage estimator? Okay, so there are various, so thank you for the question. There are various shrinkage type estimators that have been proposed. And you'll see in my analysis in a moment of the empirics that we compare to various ones. I'm trying to recall if I know the specifics of this one. So Felipe, if you have more details on exactly the form of this shrinkage, in reality, it could be that the net result is kind of similar, but that we're using a different mechanism to get there. In our case, we're using a common correlation mechanism, and very often other shrinkage methods use other parameters. And at the end, when I talk about the settings in which our method would work, you might see the distinction as to where other shrinkage methods go astray. So like, I think it's all about the various settings, how correlated the experts are, how much information you have, how well you can estimate the variances or the skills of the experts. And that's what eventually differs our method from other shrinkage methods out there. And we compare comprehensive, and you'll see in just a few slides, we compare it to not only a few shrinkage estimators like you're proposing here, but we also compare it to other wisdom of crowd techniques to kind of be comprehensive, including also MCMC and other methods for combining and estimating the parameters. And we still find that ours performs better in practice. Okay, so as I mentioned, these parameters may not always exist, and therefore we need a Bayesian estimator in practice. And our paper proposes a couple. In our paper, we propose, and I'm going to skip just in a matter of time because I want to get to the empirics, various assumptions, pretty basic assumptions that we have to deploy in order to come up with an estimator that is basically utilizing the posterior distribution for joint distribution between our correlation matrix, if you will, and the quantity of interest. And at the end of of the day with this machinery, our goal is to come up with an estimator for our common correlation, which is given in this equation down here. It's kind of a weighted average of sorts, if you will, between some kind of prior parameter and some kind of average correlation estimate. So kind of if you think about these two, so we're talking about some kind of linear combination here. This is the maximum posterior estimator, so kind of a mode, if you will. And we actually show in the paper that you can even calculate the entire distribution, joint distribution of these parameters to come up with the marginal posterior distribution for the quantity of interest. And from that, we get the mean estimator. So we actually have two Bayesian estimators. We have the map estimator, and then we have this mean estimator. Again, a slightly different variation, which again is a linear combination. And we're going to compare both of them in practice and see how well they perform. Feel free to kind of look these up in the paper. They're very, very close to each other. And what we do for the rest of the paper is we demonstrate both from simulations and from empirical data how well our proposed Bayesian estimator and a few other ways to estimate the common correlation. So how well the common correlation performs in practice, with, again, the motivation on this slide being that what we expect to see is that covariance weights are going to have quite a bit of estimation error. Simple average weights where everybody has the same weight is expected to have quite a bit of bias. And what we're hoping to see and find are the circumstances where our approach, so our common correlation, either the map or the mean approach, those two estimators that I just showed you, we hope to see circumstances where these perform better. And again, what this chart shows is the overall variance, acknowledging that we're going to kind of compromise. We're going to have a little bit of estimation error potentially because we're talking about still estimating some parameters, but try to minimize that. The data that we present our analysis on in the paper, there's two data sets actually. Some is macroeconomic forecasts, like many of you have worked with in the past. We also have a pretty sizable data set that is experimental forecasts, where individuals were asked more general knowledge type questions. The macroeconomic forecasts comes from collaboration that we had with an agency called Focus Economics. I want to highlight that the estimates that the macroeconomic forecasts, they collect a bunch of data like the Fed does or ECB, European Central Bank does. It could be that in the background, those estimates are model driven, so they're calculated from models. And so everything that I'm talking about holds whether or not your forecasts come from subjective experts' assessments and combining those versus if it's coming from models. And in fact, what the beauty is that we don't necessarily need to worry or care about that too much, because the processes that we describe are done ex post in processing. You can still aggregate information from either individuals or their models and run through the same kind of steps. Okay, what do we have here? What do we do with this data? We have basically, what we're going to do is we're going to take these data sets that are fairly large, and we're going to try and test various settings. We're trying to look at circumstances, and really what we're controlling is circumstances where our training set, and what do I mean by training? Let me just clarify again, because it might seem unusually small for this audience. When I talk about training set, I mean that there's a history of at least 4 time periods for each one of my experts. For an expert to participate in this aggregation, they need to have a sequence of 4 forecasts that they've submitted for me to be able to establish their skill and the correlation between them and other experts. And so in many settings, like the ones that I've described, experts come and go, experts participate for a while, but then leave. Experts really are not always that reliable. And we are trying to carve out history where we can find experts participating time and time again with a bunch of other experts, and we're going to take it up until 16. It is actually surprisingly challenging, especially in the macroeconomic setting, to come up with this long of a history of participation, of repeated participation by an expert. And you can see that in just the number here, the mean number of the experts with that kind of data points. It's surprisingly rare for folks, even in the macroeconomic conditions, which is pretty well established, to participate on a regular basis. And so coming up with crowds that have the same history is a challenge. And this is true, again, for many different settings where this gets done. Another interesting thing, and I realize that I'm going to be wrapping up in a moment, another interesting thing is to see, and what we tried to do is learn from these two data, say, what are the differences in characteristics between our experimental data and our macroeconomic data? And there could be several differences that emerge based on just how correlated they are in terms of our estimates of the pairwise correlation. So you see that the macroeconomic data, they seem to be more correlated with each other versus the experimental data. And that's typically the case. These are those folks who do macroeconomic forecasting typically build on similar pieces of information or use similar models sometimes. And also in terms of just the variability in skill, it's not, it's not hugely different, but you can see that on average, the macroeconomic skill set is lower. And so this is the variability in skill. And so there's a wider variability in skill among the experimental data set when we're asking them just general knowledge questions. And they're, people sometimes are very knowledgeable, not knowledgeable, versus the macroeconomic, where typically people are more similar to each other, more highly correlated and more knowledgeable of the area, of the field. Okay. We're going to check a few things, and I'm going to do this fast. First, we're going to compare different Bayesian, different estimators in general, not only our Bayesian ones, but others, different ways to estimate the common correlation, because there's different ways that we can do it. We can do a grid search. We can do, you could use MCMC. We can use a bunch of different ways to estimate our common correlation. Then I'm going to compare the common correlation method to other methods of forecast aggregation. So we're going to do both. So the first step is, how can we estimate the common correlation if we're going to use the common correlation? And what we see here is that our Bayesian map estimator performs the best. We look not only at the percentage of the cases where it does better than a simple average. That's the top table, where higher is better. And we also look at the actual MSE improvement. We also, in our paper, we also have the MAPE improvement in the appendix. So we check it on several different criteria. And again, higher is better. And we see here that our improvement of the MAP approach is the best. So from now on, we're going to mostly show results where we use the Bayesian estimator to estimate the common correlation. Next, what we're going to show here is that just looking at what that common correlation estimate is, different methods come up with various different assessments. And what we kind of found interesting is that the values that the MAP approach, the Bayesian approach does, the values for the common correlation are the kind of muted. They're actually not extreme. They're not high correlations. It's actually taking a situation where there's high correlation, but tampering it a little bit, which might be the key to success. Then we look at comparing our common correlation map Bayesian estimator to other ways to combine forecasts, the covariance weights, which we talked about, the variance weights, and various shrinkage methods, going back to Felipe's question. And we still see that by and large, our common correlation performs the best. Next, related to that, we were interested to see what the actual weight is, what kind of weight range gets assigned. And to some degree, again, we see this muted behavior where the weight that the common correlation assigns to these various experts is not too extreme. So there's not big swings in the weights. And again, that's what we believe is the source of its success. Its robustness, if you will, is because we're not talking about really a lot of weight on one expert and very little weight on another. We're actually kind of muted. So it's not quite same weights or simple average, which is equal weights for everybody, but it's not totally total big swings in the weights. And then finally, we compare to a bunch of other wisdom of crowd methods. And I'll cut to the chase and say, you can rest assured that I wouldn't do this and present it if it wasn't going to perform well, which of course it does by and large perform pretty well, with trimming being the other method that offers some benefit. And the paper also describes at the end some benefits of thinking about how many experts participate. There's this desire to be inclusive and not to leave opinions on the table, but to be inclusive in how we think about the wisdom of the crowd. A simple average is the most inclusive because we average everybody. And some of our other methods, like the top 5, which only looks at the top 5 performers, is pretty strict. And so we try to find, again, a compromise, and it feels like our common correlation method offers a nice compromise, being fairly broad in terms of the number of experts it includes in the pool, but not inclusive of not as inclusive as the simple average, which ends up deteriorating its performance. I'm going to stop there. I just want to put up my conclusion slide, and then I'll pause for questions. I know that we have maybe 7 minutes left. Hopefully, Dolores, that will help. Or that will be sufficient, and I'm happy to take questions after. So again, what is the long and short of this? We offer an approach for combining forecasts, especially under circumstances where there isn't a lot of history and the experts are likely to be highly correlated with one another. Our common correlation approach is a simple heuristic that allows you to take many different estimates and replace it with one. Therefore, you reduce the estimation error that's going to come out of it, or that you're going to be affected by. We actually propose what the estimate or a way to estimate that parameter would look like with our Bayesian estimators, and we demonstrate a few other methods. And in the paper, we also show what happens if you want, let's say, 2 common correlations or clusters. If you want to cluster a bunch of experts that are highly correlated with a bunch of experts that are are correlated among themselves, but not with the other cluster. And we show that that method can help under certain circumstances. And if you have a large group, a large crowd, a clustering method can help. And I see that James said a nice goodbye. Any other questions? Nice to see everybody. Thank you for joining the session. It's nice to see names that I recognize and new names to get to meet new folks. So Dolores, if there's any questions, now's a good time, and I'm happy to take them.
Thank you, Yael, and for this very nice presentation. And to the audience, if you have any questions, please raise your hand and we will give you the microphone and camera rights. Yeah, that was very interesting. Yael, when you say that if you have, so the samples are small, I mean, this heuristic, can you use it when this is not the case as a kickoff point, or?
Yes, you can definitely use it even when the sample size is large. And the question is, at some point, you may be able to be pretty good in estimating the pairwise correlation. So at the extreme, and this kind of goes a little bit with the clustering idea, if you're very clear on the pairwise correlation among the experts, in terms of their past errors, right? Like in terms of their forecasting characteristics, you can definitely still use this method. And it hopefully converges and it gets very close to what you would get from using covariance weights. The question is, can you calculate those pairwise correlations in an accurate enough manner? Yeah.
Thank you.
My pleasure. Would it help? I can stop sharing. I can also put, or I don't know, Dolores, if you send a follow-up with the recording or anything, I can also link to the paper so folks can kind of dig into the paper.
Yes, we can put that information, say, in the email that we sent around for the video. Yeah, thank you so much.
Perfect. My pleasure.
Okay, so to the audience, is there any question?
Any question, folks? I'll take it as everything was clear.
Yes, it was.
Crystal clear.
Yes. Yeah. So thank you so much for the talk, Yael. It has been very, very visual, and with your annotations, it was very, very dynamic. Thank you so much. And to the audience, Please remember that we are back next week again at the same time, and with another talk again from the States. So we have to be careful with the with the change of the to the winter time.
Yes. Yes, I don't remember when we're changing our clocks, but
Yeah.
yes.
So you
Yes.
see, everybody's quite happy. Yeah,
Fantastic. Good.
with the
That's
talks.
awesome.
Yeah, yeah.
Good.
So thank you so much
Thank you
again. It
very
was
much.
a
My
great
pleasure.
pleasure to see you today, and we will send around the video to the mailing list, which has lots of people registered, more than 1,800. So lots of people. Okay.
Fantastic. Thank you, everybody.